Hello, operations management students. Dr. Johnny Robinson once again. This last project management segment has to do with thinking about adding uncertainty to the expected length of time of completing individual tasks. So often when we think about doing critical path analysis, we will take each subtask as having a certain amount of time it takes. Preheating the oven, 12 minutes. Stirring the eggs and sugar, 2 minutes. We just have certainty about it, and then you can carefully calculate which is the longest one, and that's important. And we might do some project crashing on that. But reality is, some tasks might have some uncertainty to them. Turns out you didn't have the tool you needed, or the part that you got needs to be repaired or adjusted, or your machine needed to warm up, or who knows, all the random things that could go well or poorly. And so it's worthwhile to think about adding some possible variability. And there's lots and lots of ways to do this, but one way that I think is really pretty intuitive, that is common practice, is to think about coming up with a distribution around the potential outcomes and describing it with like an optimistic time or a pessimistic time. And the way this is generally described, as you say, is to say, okay, out of 100 times, what's going to be the slowest one and what's going to be the fastest one, right? What's your 99th percentile and your 1 percentile for time? So you'll have one that's pretty long and one that's pretty short, and then you'll have a most likely time. And those don't have to be symmetric. So you can see in this example the pessimistic outcome is 30 and the optimistic outcome is 15, but the most likely isn't 22.5. It seems to be something like 24. So this distribution is a little left skewed. So it doesn't have to be perfectly symmetric, but we can specify it just with those simple numbers, right? So you get this kind of bell curve you're defining. So if we define a P for pessimistic, O for optimistic, a good way to get an expected time is to use what's called the PERT beta distribution. And it's just simply this, right? Optimistic time plus pessimistic time plus 4 times the most likely time divided by 6. So it's a weighted average of those 3 things, right? And you'll notice, right, this is like 1 O, 4 M's, 1 P. That's 6 letters divided by 6 gets you your average letter score, right? And so I've got an example I'll flip over to here. So if I go to this, right, you're familiar with this network from if you've watched the previous video. But here we've got, right, this task A, so it's got a most likely time, but it could be slower by 2 or it could be faster by 1. And so I'm just going to do that math, right, that we had to find that average time, expected time. So I'm going to say, okay, so I want optimistic time plus 4 times most likely time plus pessimistic time divided by 6. I get some numbers, and I can drag that down. So again, that looks like this, right? Optimistic, 4 times most likely. Pessimistic, 6 of those, divide by 6, get your average, right? And so we can see that, we've got a lot of decimal results here, right? So, right, this is a little bit longer on average because we're acknowledging that sometimes it doesn't go well. Right, let's see if there's any. This one's a little bit faster on average than we were predicting because, when it has a lot of potential to be quite a bit faster. So this, often you can think about these, an example of this would be like a search task, right? If you're looking for something and it's there, you're definitely going to find it, but you might find it really quickly. But you can guarantee that you'll find it at a certain point because you've checked everything, right? So we have now these new average times. So then when we do critical path analysis, you actually want to do critical path analysis on the average time. So when we used so before we just had our most likely times that we were just using. So we got KLHD as the critical path. But now we can use the same cells, right? Because these are using these letters, right? So I can just copy and paste this to use column J instead of column G and get new average estimates. Let's see, right? So ABCD took a little longer, 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 and a little shorter. So this compresses it a little bit, but it is still true that KLHD is our critical path. So we can leave that bold, that's fine. So it doesn't seem like we've done anything interesting yet, right? We still say KLHD is our critical path. The numbers have changed a little bit, but that doesn't seem to be all that particularly compelling. What this does get us, though, and this is where it really starts to do some work, is we can get some high and low times for this path. So if I think about here, let's do high and low. Right, KLHD, we can just add up the KLHD pessimistic times, or K plus L plus H plus D pessimistic. All right, so it could be as long as 23 or as little as 1, 6, 3, 1, 11. Right, so there's a lot of variability here. Here's the thing, though, right? This was a 1 out of 100 chance of getting 9. 1 out of 100. That's pretty unlikely. But what's really, really unlikely is getting 1 out of 100 bad in L, 1 out of 100 bad in K, 1 out of 100 bad in H, and 1 out of 100 bad in D. That's astonishingly unlikely. So we don't... This is not... Right, this is a time... Right, 9 is a time that might happen. 23 is a time that it basically will never happen. So what we need to do is be more sophisticated than this. This is not really enough. And so what we actually would rather do is come up with the standard deviation of completion time. And so to do that, we need the standard deviation of individual tasks. And so so we don't want that for paths yet. So I'm going to move this out of the way here. And we'll go, so now standard deviation. So there's a formula for standard deviation as well, and it's similar, right? It's really optimistic minus most likely plus 4 times, most likely minus most likely plus pessimistic, plus pessimistic minus most likely, all divided by 6, all right? Because we want to know the distance. But you'll see right away, though, this is just going to be 0, right? This is just going to be 0. And, right, these will cancel in a way because this is going to end up negative. And so we can just basically simplify this to be optimistic minus pessimistic. And you get to the same, that's really what's going on here. So, I need another parenthesis there. Oops. So optimistic time minus pessimistic time. Oh, only backwards, right? Only backwards. Pessimistic minus optimistic. H minus I. There we go. And so we've got, right, so this is saying, well, 7 is likely, but one standard deviation up or down would be 7.5, 6.5, 8, 6, right? Whereas this one has smaller standard deviation. And then variance is just the standard deviation squared. That doesn't have as easy an interpretation. What it does do, though, what variance does do, is for these critical paths, right? It's a statistical property of adding uncertain things. When you add tasks, right? Basically, any random number. If I add random numbers together, the distribution of the sum has a variance that's equal to the sum of the variances. So once I calculate this variance, which again was just this number squared, then I can add up the variances. So I'm just going to say K plus L plus H plus D, and I'll get a variance number here. This turns out to be 1. And then the standard deviation is the square root of this number. So I should be able to just copy and paste this, right? And then this will go here. So we can see, even though, so KLHD is the critical path, it also has the highest uncertainty of all the paths, right? And ABCD, which is very close, has an uncertainty that is still pretty high. So you can imagine, right, if this, it's very reasonable that the KLHD could take, 17, right? That would be within one standard deviation of only taking 17. And ABCD could take 18. That would be within one standard deviation. And so if you get, unlucky with ABCD and lucky with KLHD, your critical path can be off. That's not true exactly, because critical path is, I guess a theoretical, like this is the one that takes longest on average, right? But I guess what you might ultimately observe is that the ABCD path takes longer, even though it's not on the critical path, because there's some uncertainty here with how much they go. So yeah. Point is, though, if you've got these triple time estimates, you can find the average time using this formula. Pessimistic plus 4 times most likely plus optimistic divided by 6. Standard deviation, pessimistic minus optimistic divided by 6. Square it, and then add up those variances for the critical path, and then square root that. So that's how you do it. It's kind of roundabout process, but yeah, that's how you get there, and that's how you would get a picture for the, if I was to draw a bell curve of the time it takes this KLHD path to complete on average, right? It would be centered on 17 2/3, and then would go up to 18 2/3 and 19 2/3 at the high end of the tail, and then 16 15 at the low end of the tail. And that can matter for, like, for example, if you have a contract provision that kicks out penalties if you don't complete by a certain time, you can say, okay, well, we know this is going to take 17.6 on average. What's the probability that we can complete it by 19? Well, then you would just say norm inverse, norm dist, and we want to see, 19 with an average of 17.66666, standard deviation of 1. So that would be a 90% chance that we would get that done in time. And maybe that's not good enough, so then we might need to do some crashing. So if we could get it down to 17.333 maybe, now we're up to 95, right? So that might not be, again, that's only crashing 1/3 of 1 hour, so it might not actually be that expensive to do. So So yeah, that is triple time estimates and calculating overall project standard deviation.